Hey guys, I wanted to discuss one problem in your university model question paper on discrete mathematics. So this question is asking about the proof that rational numbers are countably uh, infinite. So I'm making this video to explain how to answer this question. So there is one topic in our syllabus which is uh, Cantor diagonalization argument. So we'll be using this uh, Cantor diagonalization to answer this question. Now we know rational numbers are of the form p over q, where both p and q are integers. So what this means is when they say countably infinite, that means you can count all the rational numbers. That there are infinitely many rational numbers, but you can count them. Or in other words, what that means is like map you can map every rational number to a unique natural number. So that's what it means. So it's in terms of functions. If we can call it a one-one mapping, and also an on-to mapping, which means if there is a rational number, I can map it to a unique natural number, and if there is a rational number, uh, yeah, so it means if there's a natural number can be mapped to a unique rational number, and if there is a rational number, it can be uniquely mapped to. There will be a natural number to which maps to that rational number. So, for example, it means if I can assign, there is a rational number 1 over 2, and if I map it to 1, then for another rational number, I'll be assigning another number 2, like 1 over 3. So, 1, 1, and on 2 means you can always find a, a natural number mapped to a rational number and vice versa, which means if there is some rational number here, 4 over 3, you can always map it to a natural number in the domain of natural number. So that's what it means when they say it's countable. But we already know that the the natural numbers itself are infinite, because there are infinitely many integers, and so there are infinitely many rational numbers that you can form using those integers. So now coming to the proof for this. So this is a systematic way of how you can go about proving this. We can think about one, and then we can start listing all the rational numbers which I can form with one as the numerator and other integers as the denominator. I can say 1 over 2, 1 over 3, 1 over 4, 1 over 5, and I can keep going. So since we have infinitely many natural numbers, we can always form fractions of this form where numerator is 1 and the denominator is all the different natural numbers that we have. Now if I go to all the rational numbers with numerator 2, I can start listing them like this. I can list them like 2, over 2, right? 2 over 3, 2 over 4, 2 over 5, dot dot dot. Now, for all the rational numbers that's with numerator 3, I can list like 3 over 2, 3 over 3, 3 over 4, 3 over 5, dot dot dot, and I can keep going like this. So, like when we list it like this, we can immediately see that we are listing all possible rational numbers by doing like this, because we first list all the rational numbers with numerator 1, and then all the different natural numbers that can go as the denominator. Now, similarly, we list all the numbers with numerator 2, and then all the natural numbers which can go into the denominator. So when listing it like this, we can immediately see that uh, the rational numbers are actually like countable. Like we are not missing any rational numbers here. But to argue with the Cantor's diagonal argument, we have to follow, like, to make sure that we are not missing any natural numbers. We're visiting every possible rational number. We What we do is this: we first go to, right. So this actually, this is like 1 over 1. This is 2 over 1. This is 3 over 1, and like that. So now what we do is first we move in this direction. So let me change my color here so that, like that, right? Then, so we are starting from 1 and we have moved to 2. Now look at this. So now what I do is I draw this diagonal. So the numbers along the diagonal are, like, I can always list them as ordered pair of numerator and denominator. So like 1, 2, and 2, 1, right? And see that they sum up to 3, right? So we start with 1, and then we are now looking at the diagonals, right? Now if you look at the next diagonal, right? So that looks like this, right? Now if you list them as ordered pairs, it looks like this: 1, 3, and 2, 2, and 3, 1. So they all add up to 4, right? So uh, like visiting all these numbers along these diagonals, like here it will be like 4 over 1, so which will add up to 5. So this will ensure that we are not missing any rational number in this list, and also we can be sure that we can, like, map a natural number to a unique rational number. So to show that, we can, like, for example, I can say the first rational number is 1. I can map it to 1, right? Next number, I can say the second one is 1 over 2, or let's say 2 over 1. Third one is 1 over 2. The fourth one is 1, like, which is the other number. So we can say that fourth one is mapped to 1, 2, 3, 4, 3 over 1. Right. So again, keep mapping all these rational numbers to a unique natural number, and then what we also do is we like skip numbers which repeat. Like we already have 1 here now, right? So if I now try to map the 5 to a rational number, like we won't map it to 2 over 2, because one is already one has already been mapped. So I'll map it to, like, the next number, which is 1 over 3, right? So this way I can ensure that mapping I can find a unique mapping of a rational number to a natural number. And so now, so that's the, like, argument for the fact that all rational numbers are there are infinitely many rational numbers, but you can always like count them. So if you list these rational numbers, we can be sure that you are not missing any rational number because there is always a mapping. There's always a unique mapping of one rational number to a unique natural number. So hope that explains uh, the proof for that problem. And so this is how you have to like argue, uh, like this is how you have to like prove, write the proof for that question.